All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's actually jump right into it, shall we? Because we were sort of in the middle of stuff last time. There we go. So we're still in our, shall we say, exploratory phase. We're exploring a new concept, learning about a new concept just in terms of definitions and how things work. We'll do more of that today, more of the same, pretty much all day. We'll actually get to some examples for next class, which I'll leave for you guys at the end. But for now, we're just going to learn more about what we did yesterday, which is sets. So we started talking about sets. Sets are very important to understand in general, but we need to understand them for our probability, what we're going to be doing in probability. A lot of it will be about first visualizing things as sets and then learning how to count things in those sets, etc. That's going to be very important. So a set is just an unordered collection of objects in which repetition is ignored. So that's basically it. I gave the A or B and B example, and as well as set notation, the roster method, very common method, and it can be modified to suit our needs. We think of sets as being equal if they have precisely the same members. We also defined something called a tuple, which is a set where we do care about order and we do care about repeats. And so we might want to look at things like that. I gave the example of grades in a class might be such a thing. You definitely want to know which number applies to which grade, which was the first test taken, which was the second test taken. And of course, you can get the same grade twice and you want to count that repeat. We also looked at things like the size of a set, what that means, finite set and infinite set. These have very intuitive definitions, right? So if it's a finite set, I think you would kind of know what it is. But for us, it just means the number of things in it is what we call a natural number. I'll talk about that a little bit today. So if you can define how many things are in this collection with a zero or a positive whole number, like there are 17 things here, there are 53 things here, there are a million things here, we call that thing a finite set. Every other kind of set is called infinite. There is the empty set though, the set with no elements. That guy is written as a zero with a slash through it. And there's the concept of a subset. Sometimes a set, of course, is a collection. And what we want to do is we want to make a sub-collection. We want to make a collection from the previously made collection. This sub-collection is called a subset. It's potentially equal to the original set. It's also potentially equal to the empty set, right? It's possible that I want to take nothing from this previous collection. It's important to know that the empty set is a subset of every set, and every set is a subset of itself. Also useful to know that two sets being equal also means that they are subsets of each other. We did some examples about that. Then we spoke about power sets. This is the set of all possible subsets, which is important for a lot of reasons. We found some of the power sets. We looked at the size of the power sets. We know that if we have a finite set with n elements, the power set of such a thing is going to have 2 to the n elements. And the reason for this was something called the multiplication rule, which we'll talk about more next week. We're not going to talk about that much right now, but that's the idea. The idea is for each element, you have 2 choices. And if you want to know how many possible sets you could create from that, then you have to multiply all the possible choices for each element. And so that's called the multiplication rule. About figuring out all possibilities comes from figuring out all the choices that you have in every stage and then multiplying all the choices. That's called the multiplication rule. And you can use that to figure out how many things are in the power set. So I just wanted to introduce that idea. It is an idea that we will be returning to and looking at in a little more detail next time. But that's where we ended. Now, we're going to do more of this. So it's another lecture of just me just kind of telling you definitions and telling you how stuff is going to work. And starting next class, we're actually going to do problems with these things. So yeah, let's do that. Let's jump right in. The next definition I want to tell you about, told you about that already. Numerical equivalence definition. sets A and B are said to be numerically equivalent. Now, in text, we often would leave off the word numerically, but usually if you're like speaking to someone, you would say numerically. And that's because equivalence and equal, people often mix that up in their heads. They often say one when they mean the other. To be equivalent and to be equal are not the same thing. So sometimes we emphasize this by saying the word numerically in front of it. So two sets are called numerically equivalent if the number of things in one is the same as the number of things in the other. Now, they do not have to be equal for this to be the case. So let me just give you an example. Suppose A is a set 1, 2, 3, and B is the set A, B, C. What a squiggly bracket that was. Then, of course, A does not equal to B, right? They are not equal. They don't have the same elements. However, but the number of things in A and the number of things in B are both 3. They have 3 things in both of them. They are numerically equivalent. So they're not equal, but they're equivalent. So equivalent and equal, they don't mean the same things. Equivalent just means they have the same number of things, which in and of itself is actually a very important thing. It turns out in mathematics, there's this concept of isomorphism. You don't really need to know about that word. We're not going to really use it. But the idea is that there are times when you can be in several different contexts and you're dealing with different sets of things. And really, you're really dealing with the same set of things. You just don't realize it yet. You haven't discovered that this is actually something I've studied before in a different context. It's just that in this new context, I didn't recognize them. So it's like you can take a group of people who live over here, you can put them through witness protection, you can change all their names and their appearances, and you can relocate them over here. And then you go and meet those same 10 people over here, and they turn out to be the same 10 people. They look different, they have different names, but you start talking to them, having conversation, you realize, hey, this guy behaves like this other guy I knew over here. Like they're actually the same guy, right? And so a lot of times in mathematics that shows up and you want to know when that's happening. One of the first things you would check is that there's the same number of things. It's very strange that there are 10 people who behave like this over here, and then suddenly there are exactly 10 people who behave in exactly the same way over here, right? So sometimes knowing how many things there are is a very important thing. And so we want a concept to capture that. You would not think of them as the same thing. If there were 10 people over here and there were 12 people over here and they behave very similar, you won't automatically assume that, oh, they must be from the same group, because obviously they're not. There are 10 people in this group and there are 12 people in that group. They're obviously not the same. So the number is going to be the first thing you're going to want to check. So just thought I'd mention that. Let's talk about some common number sets and their equivalences. Now, I'll give you, there will be some examples we have to do with these guys, but for the most part, not really. But it's very important that you know these guys so that when I talk about them, and if I like write down certain symbols, you'll know what I mean when I write down those symbols. So we do want to talk about some important numbers. First, here's a symbol that you saw me write yesterday. It's like it's called boldface N. That's how you write a boldface N in on paper. This is defined to be this set going on forever. It's called the natural numbers. or the counting numbers. Usually they call it the natural numbers or the counting numbers. It's very natural to count with these guys. So that's them. I will say a warning here though. It can vary based on the source, what people mean when they say the natural numbers. However, usually in such a case, there's going to be a glossary. If anyone does a lot of work with the natural numbers, they'll usually have a glossary or somewhere in the source material, they will tell you what they think the natural numbers are. But there's times when people leave out 0. So you might have to be a little bit careful. For us, though, we want to include 0 because we have the concept of an empty set, which has 0 elements. So we want to be able to count 0 elements in a strange way. We want to have some mathematical language for that. And so basically, we want to be able to say a finite set is any set with cardinality in the natural numbers, right? So a natural number describes its cardinality. And so the empty set will be considered a finite set by this definition because 0 describes its cardinality. Remember, cardinality is just another name for the size of a set or how many things are in the set. So these are the natural numbers. It's an infinite set, right? Like you can keep counting forever. Now, you might be interested in including the negatives. And in such a case, you end up with what we call the integers. So I might want to throw in the -1 and the -2 and the -3 and so on and so forth. And this is called the integers or the whole numbers. Why do we use Z to represent the integers? Well, it's from the German word Zahlen, which means number. So that's where the etymology comes from. Do you call it etymology when you talk about symbols, or is that just words? I don't know. Another guy is Q. Q here stands for quotient. Quotient means division. So these guys is a set of things that we get by dividing. Dividing what things? It's hard to list out every element here in some reasonable way for you to get a pattern. So we usually define this by a condition. It's everything that looks like A divided by B, where A and B are integers and B is not 0. This is the rational numbers. We call them the set of fractions. So if you take one whole number, divide by another, you get what's called a rational number or a fraction. Division by 0 is not allowed. So the guy in the bottom can never be 0. However, other than that, there's really no restriction, can take any number and divide by any other number. And 0 can be in the top, that's fine. And you get the set of fractions, all possible fractions. We call these the rational numbers, and these are represented by Q. So next, we'll put a little line here because we're going to cross a threshold, which you may or may not know exists at this point. And let's talk about R, the set R. This is the set of real numbers. Now, this one is actually very, very difficult to describe. If you're a math major and you took all this math and you're at this point, you're at like calculus 4, you've already done more math than almost anyone would have done in their lives. And at that point is when we start to describe to you, okay, here's what numbers really are. Here's what the real numbers really are. Those guys you've been playing around with the whole time, and you can start to describe them. So really, you're like, unless you're like reading ahead, you'll be a third-year math major before you really start to understand what numbers really are. and what real numbers really are. And it's very complicated to define them. You define them with things like data kind cuts and completions and Cauchy sequences and all sorts of things. But so there's really no good description of the real numbers that I can give you other than the intuitive descriptions, which can't really count as a definition, but it will count for a definition for us. Something like the set of all possible decimal expansions. Or something like the set of all points numbers on the number line. So you draw a number line. Of course, you can mark down the integers on it. You can mark, okay, here's the 0, here's the 1, here's the 2. You can mark down all the fractions on it. Okay, here's a half, here's 3/4, here's 15/17. You can do that, and but you're going to miss certain gaps when you do that. And any other number that can fit is called is a part of the real numbers. We then also have the complex numbers. This one I can describe. Once you get through over the hurdle of describing the real numbers, which is literally one of the hardest things to describe in mathematics, which is strange when you think about it. Like, a lot of people think that math is all about numbers. It's not, but a lot of it has to do with numbers, and the real numbers is something that we use all the time. So people would think, oh, it's probably a very simple concept. It is not. It's very difficult to actually describe the real numbers in detail, in totality. So if an alien came to Earth and asked about our number system and says, oh, you have something you call real numbers, describe that to me. It would be very, very hard. It actually won't be too hard to describe integers to an alien, but to describe the real numbers, it's going to be, yeah. It's everything on this line right here. It's going to be like, but there's nothing on that. I just see the line. So this guy here is the set A plus IB, where A and B are real numbers. I is the square root of -1, which we invent a number to be that describe that. So we like these guys because it allows us to take square roots of negative numbers and things of that sort, and it gives us a whole other dimension to the number line. So it gives us a vertical axis on the number line and then creates an entire plane of numbers. This is called the complex numbers. Of course, we don't talk much about the complex numbers in this class. I guess I would mention them because they're very famous. So that's the complex numbers. We need them to solve a lot of problems because it turns out that the real numbers, there are a lot of them, but they aren't good enough because we're not able to solve every equation with them. So not all polynomial equations will have solutions in the real numbers. For example, x squared plus 1 equals 0 has no solution if x is only thought of as a real number. It does have a solution if x is thought of as a complex number, though, and that's important. Their equivalencies. And this is where things can start to get kind of strange, which is why we are not going to be dealing with infinite sets very often. But I do want you to know how these infinite sets relate to each other. And when these things were first discovered, like I was telling you about the tragedies of set theory, yeah, when it was first discovered, it was kind of very, very strange, and not everyone accepted it. And the people who purported these things were not treated very nicely by the rest of the community. Luckily, we're beyond that now. I don't know. We might be going back. We had a lot of free thought where someone could, have an opinion and justify that opinion, and everyone would listen. We've had a lot of that for a while. It's kind of going away again, but back in the day, that was there. And if you said something that not everyone agreed with, they didn't treat you very nicely. And so you had a lot of these brilliant mathematicians who use their knowledge today to accomplish amazing things. But at the time when they came up with that knowledge, it was not accepted and they were ostracized for it. And yeah, wasn't a fun story. And you would think that it's about numbers. How heated can people get? Human beings can get quite heated at any opinion. So here are some things that were figured out. The natural numbers are infinite, but we figured out that, you know what? There's the same number of them as there are integers. So you take the natural numbers 0, 1, 2, 3, 4, 5, going on forever, and let's add to it another infinite set of numbers, -1, -2, -3, going on forever in the other direction. It turns out you haven't actually added any more. You have the same number of things, right? Which is why I put number in quotations when I was talking about cardinality the other day. You wouldn't make a difference, actually. You have the same number of things. On top of that, when you take all these numbers and then you start to divide them and get all these new numbers. So now you're throwing in the halves, the 3/4, the -11 over 17, the -243 over 1297, right? All those things. You start throwing these guys all in, you get the rational numbers. Turns out you still have the same number of numbers, right? So those infinities are all the same. And a lot of people thought, well, yeah, infinity is kind of like a concept, right? It's not really like something that can have a property. We think of infinity as just something that means more than you can possibly have. And that was kind of how we thought about infinity until set theory came along and we realized, actually, no, there are varieties to infinity itself. There are different kinds of infinities. There are infinities that can be larger than other infinities by a mind-boggling amount. And that showed up here with numbers. It turns out that these we know is much less than how many real numbers there are. Now, the real numbers are the completion of Q. So you would realize that you cannot write a number like the square root of 2 as a fraction. You cannot write a number like pi as a fraction. So if you were to write down, draw a number line and list all the fractions on it, it will miss certain things. There will be gaps in certain spots, gaps where you couldn't put numbers that are fractions. And these numbers are called the irrational numbers. And they're what you fill in. These are what the real number, you throw into the real numbers to complete the number line. So it's called the completion of Q. And it turns out that filling in the gaps, there are actually more gaps than there were numbers in the first place, which was very strange because we actually knew before that there's an infinite number of fractions and there are so many that no matter what spot you look on the number line, you will find one. You take the number line, you take any interval on the number line, no matter how small, there's going to be a fraction in there somewhere. And if you take any two fractions, no matter how close together, there's going to be another fraction in between them. In fact, there's going to be an infinite number of fractions in between any two fractions, right? So it's like you would think that the fractions kind of fill up the number line, like there's hardly any gaps left. But it turns out that there are way more gaps than there were fractions in the first place. It's amazing to know that the gaps, you missed more of the number line than you have completed if you only take the fractions. When you fill in all these gaps and you get the real numbers are actually a larger infinity. The size of the real numbers is a larger infinity than the size of the fractions. And it's larger by a lot. It's larger. It's a worse comparison than comparing a single drop of water to the entire ocean. The real numbers is bigger than the set of fractions, even larger than all the oceans in the entire universe is bigger than a single drop of water. It's that mind-bogglingly huge. It's a huge infinity compared to this other infinity. And when this was proven by Cantor and guys of that caliber, people that couldn't accept that, like, no, like one infinity can't be that much bigger. It's like nothing. Are you kidding me? And of course, this tied into the concept of God that, there's this thing out there that's bigger than anything else. And then set theory came along and said, well, no, there is nothing that's bigger than everything else. We can always get bigger. There's always a bigger infinity. And so people really didn't like this. And so it turns out, yes, there is a bigger infinity by a lot. Like I can take all the real numbers, like the real numbers can go on a field trip, all the fractions can get lost. They'll do a head count and be like, oh, I guess everyone's here. Let's get back on the bus. They would not notice them missing. It's that huge, right? Now, you would think, all right, so all the numbers on the number lines are huge, right? But what if I created an entire 2D plane and then every point in that plane? Now the line is in that plane and it's not in all the space. So the set of all points in this space must have more points than is on a single line that's in that space. Turns out that would be wrong. The set of complex numbers is the same size of infinity as a set of real numbers. It turns out this infinity is huge. It's very hard to escape it. Well, not really. If I take the power set of like a set of real numbers, so I put real numbers all into each set of their own, take the union, and then take the power set of that set, I get something that's larger than that infinity. That is as larger than the real numbers as the real numbers is larger than the fractions. It gets really crazy. But yeah. Anyway, I introduced that mostly to introduce things like this. When I write down things like this, I want you to know what I mean when I write down things like that, as well as I'll give you a few examples. It's going to be useful to, because you're used to numbers, it's going to be useful to play around with numbers to get used to certain concepts that I'll be introducing in a little bit. So knowing about numbers is going to be important. But yeah, all these sets are infinite sets, but some infinities are bigger than others. And it gets really wacky, really crazy, really fast. I mean, you take up a set theory book, and this is the kind of knowledge that they hit you with on, like, in the first chapter, really, like in the first few pages, and it gets a lot crazier than you can imagine right from there. So here, let's get back to Earth. Let's get back a little sane, and let's just talk about something small like a universal set. So I want to talk about the concept of a universal set. So it turns out that in mathematics, we never really think of anything as in like a vacuum, right? So it's not like we can create a set and, you know, now we just have a set. Every set is considered to be from somewhere. Like there's this universal set in the background, and every time I create a set A, I took those elements to create that set A from this universal set. So A, there are all these things that live in a universe, and I can pick things from that universe to put into my set. That concept of the universal background is called a universal set. Every set is considered to be a subset of some larger, potentially larger universal set. So there's always this big set in the background, right? So it's not like, oh, I discovered a new element, carbon. Yeah, but that element exists in a larger periodic table. There's a table of elements in the background of which you've just found a single example. And you can create groups like, you know, I don't know why I'm giving that example. This isn't really a science class. Because I'm teaching another science class. But yeah, you can find an element, but there's a larger element always in the background. You don't just find a list of metals and think that, oh, metals are all there are. No, the metals are just examples of things in the universe. So that's what a universal set is, right? So sets are always considered to be, even when they're not stated, it's kind of like this thing you know in the background, always be considered to be subsets of some potentially larger set. In the background. This set is called a universal set. I do want to emphasize the A here because universal sets are not unique. There are varieties of universal sets. Universal set is just your chosen universe. You choose the universe you want to work in. and then the set of all things in that universe is the universal set. And now you create sets from that universe. So that's called a universal set. It is denoted by U, uppercase squiggly fancy U. I'll talk a little bit more about this in a bit. For now, let's give a definition. The complement of a set A. This is a set of all elements in U that are not in A. So I have a universal set of things. I pick a bunch of things and I create a set that I want to work with, the set A. Everything that was not picked, that I left in the universe, we say is in the complement of A. It's the complement to A. This is denoted by A with a little C in the top right corner, or A prime, which if you're in calculus, that's going to cause a lot of confusion, but we're not going to be doing calculus in this class, or A bar, and is read the complement of A. Or more commonly, A complement. All right, so that's what we usually call it. So when I say A complement, this is what I'm talking about, this guy. Yeah, you should know how you should say it, because, you know, it's important to sound like you know what you're talking about, whether or not you know what you're talking about. Let's actually do a little example here. Example. Let's say my U is 1, 2, 3, 4, 5, 6. So for the purposes of some problem, I decide that my universe, all possible things in existence, there are just 6 things, and it's these 6 numbers. And then, so now I have a set A, which I can think of as 2, 5, 6, right? So it's not like yesterday I wanted to say, oh, A is the set 2, 5, 6. Now it's like, okay, it's the set 2, 5, 6, but it's the set 2, 5, 6 that came from somewhere. It came from this universe. And now I can say, well, what would be in A complement? Well, A complement will also be a set, right? So a complement is also a set. Set of all things that are in the universe, but not in A. So you'll notice that 1 is in the universe, but not in A. 3 is in the universe, but not in A. And 4 is in the universe, but not in A. So that is a complement. Yeah. Let's talk about Venn diagrams. So we want to talk about visualizing sets. A Venn diagram. The Venn is usually capitalized. It's one of the few cases where, because it's named after a person, it's one of the few cases in math where something is named after a person and we keep it capitalized. I don't know what the history of that is. There are a lot of things that are named after people that we use it so commonly that we just don't capitalize it anymore. But Venn diagrams, the Venn is always capitalized for some reason. Named for John Venn. And I did confess to my class, I don't remember that for sure that his name is John. I think it's John, but I didn't have time between that class and this class to actually look it up. But I think his name is John. It's named after a guy named John Venn. It's a way to visualize sets within some U. It consists of course, a universe. This is a box, and as well as sets in that universe. Which we usually represent by circles or ovals. Okay, so example, with my U above being 1, 2, 3, 4, 5, 6, and my A was, I believe, 2, 5, 6. I could represent this via a Venn diagram. I could say, draw a box, and that represents the universe. Then there's a circle living in that universe called A, and everything that's in A, I put inside this, this circle. So 2, 5, and 6 would live inside this circle, whereas 1, 3, and 4 would live outside. And that's a Venn diagram. However, usually we do not list members in Venn diagrams. But rather use them to keep track of cardinalities. So in the above, notice that the size of your U was 6 and the size of your A was 3. The Venn diagram would be instead, or maybe I'll do. I don't want to use the numbers in an example where I already had numbers. So let's actually do this with a different example, but equivalent example. Example, U equals A, B, C, D, E. Let's just use that. A equals A, B, C. Then the Venn diagram would be, here's A, here's U. But I wouldn't actually write out A, B, C, and D and any of that. I will just say how many things there are. So in A, there are 3 things. And there are 3 things. And in the universe outside of A, there are 2 things. So in total, there are 5 things. So there are 3 things in A, specifically A, B, and C. There are 2 things outside of A, specifically D and E. But you don't really write that. You actually just write down the numbers. So here, 3 elements in A. And here, you have 2 elements in a complement. And then you have a total of 5 elements in the universe. Okay, so usually you use Venn diagrams to keep track of how many people there are in each situation. Because here, the size of my U would be 5, the size of A would be 3, which of course means the size of A complement, all the guys that were left over, would be 2. And so that leads to Venn diagram. So you draw it based on cardinalities. For now, that's all the descriptive definition stuff I want to tell you about sets. Right now, what I'm going to do is I'm going to define some set operations and then leave you with some examples to try for next time. So set operations. So we know what sets are. We now know how to visualize them. So what we're going to do now is talking about let's actually do stuff with our sets. Let's actually do math with them. Can we do calculations with them? Can we combine sets, subtract them, add them, things of that sort? So that's what we're going to talk about now. Set operations. At the moment, there are two that I want you to realize, three that I want you to be aware of. I might throw in a couple more later on. So let A and B be sets in some universe U. Definition. The union of A and B denoted A U B is defined by A union B is a set of all things such that X is in A, or X is in B, or X is in both. So the union is just an amalgamation of sets. You combine them all. You take all the sets, you put them all together in one set. Anyone who's in either one of these sets gets to be put in a set. If anyone is in both, then remember, we ignore the repetition, so you don't really list them twice, but you combine everyone. This is combining sets. This is red because we need to sound like we know what we're talking about. A union B. So you don't say A U B. No one's going to know what you're talking about. Say A union B, and I'll know, oh, this they're talking about combining this. This person knows what they're talking about. Okay. Define another one. As for the examples, we'll see them next time, where you can see me playing around with these concepts. There's a concept of an intersection. It looks like an N, but it's not really an N. It's like that. A union B. A intersect B is defined by A intersect B equals the set of all X such that X is in A and at the same time X is in B. As the set of elements A and B have in common. It's red. A intersect B. So we want the guys that are in both sets at the same time. This might in fact be no one, in which case the intersection can be empty. If A intersect B is the empty set, we call A and B disjoint. That'll be important later. So A and B can be disjoint. They have nothing in common. That's totally possible. Let's talk about the third operation I want you to know, set minus. We define a set A minus B or A backslash B. This is more archaic. This isn't used much anymore. Anyone who uses that is probably classically trained. Oh, I went to Oxford in the 1960s. Okay, they would write it like that. But the kids these days write it just like with a minus sign. by A minus B is the set of all elements such that X is in A, but at the same time, X is not in B. So you take all the bad guys in A, throw away all the guys that are also in B. Yeah, red, A minus B. But the minus here doesn't work like it does with numbers. Like you can't get like a negative set, like you can get negative numbers or something like that. The worst you can get is the empty set. And the answer is a set, it's not a number. Let's visualize the above. So we can talk about A union B. And how that is visually represented is everyone in A or B or both. It's a combination of them. I also want to mention we draw Venn diagrams with as many overlaps as possible. In general, except if we know, and you have to have a good reason to know, there are no overlaps. If there are none, but we drew overlaps, it's not a problem. We would just label them like 0 to say there's nothing in this overlap, even though I drew it. So drawing my A and my B circles completely separate, not overlapping, is not good in general. Because if there is an overlap, you won't be able to represent it on your Venn diagram. But if there isn't an overlap, either one will work. So you must know A and B are disjoint to do this. Okay, so that's just a general concept. So in general, we will draw as many overlaps as we can. So with 2 circles, there's going to be 1 overlap. For the intersection, this means all the guys are in common, all the guys that live here. For the set minus, if I look at A minus B, it's all the guys that are in A, but not in B. Could go the other way around. I could talk about B minus A. And it's all the guys that are in B that are not in A. It's also nice to visualize a set and its complement, so let me do that. This is A. A complement. So A is, of course, everyone in A. A complement is everyone outside. Right? Now, being able to illustrate sets is going to be very useful in coming up with solutions to problems, even though the picture themselves can never be solutions to problems unless the problem is to draw a picture. But you can't really prove anything with pictures. In math, we know better that human perception is actually very flawed. Just because someone has a nice presentation doesn't mean that they're saying the right thing. So we can't prove things with pictures, but we can illustrate them. anyway, that's pretty much all I wanted to say for now. So I'll leave you with these examples to try for Friday's class that I will leave in the notes right here. But that's where we are for now. So I want you to use Venn diagrams to kind of conjecture what the relationship between these sets are. Again, it's not going to be proof, but it is be good enough for us. Then here are some things where you get to practice finding intersections and unions and set minuses, and more intersections and unions and set minuses. So we will do this next time. I will leave these guys in the notes. But for now, we will stop there. Next time we'll do these problems. We'll also probably do some problems from Venn diagrams, word problems that you would use Venn diagrams to figure out, and we will take it from there. Thank you for your attention. I will leave you there now, and I will see you guys in the next one. Ciao.